For our project, we designed an autonomous tortoise that acts as a pet for the purpose of entertainment and evoking a positive emotional response in users. Using computer vision, the tortoise will detect a human wearing a particular color and follow them until they are out of view. Once out of view, the tortoise will stop moving and hide in its shell.
We used a rack and pinion to create a retracting head. The pinion is attached to a servo motor and fixed in place, while the rack is free to move back and forth along a rail inside the shell. There are 6 arms attached to the rack. The wheels on the bottom track keep it up, while a wheel on the track above the head makes sure that the weight of the head doesn't cause it to lean forward. This way, the head is always in alignment with the hole in the shell, and the head will be able to easily pop in and out. The whole head is hollow, letting us run wires through the rack up into the head where the camera is. This way, the wires are neatly tucked away, and we don't need to worry about them getting tangled up in all the moving parts. The retracting head not only makes the robot more entertaining, but is also a visual cue for the users to be able to tell when the camera can and cannot see them.
Now, for the mechanical aspect of the robot, the team decided to make this general setup. It consists of the head with the rack and pinion for the retractability feature of the robot, the shell where the head actually retracts to, and it also serves as pretty much an electronic component housing unit, bottom panel where the electronic subsystem is attached to or connected to, and the legs for the actual mobility feature of the robot so the robot actually moves around. Here we have CAD screenshots for the shell, the bottom panel, and the updated legs. Now the front 2 wheels have motors attached to them in lieu of the team deciding to do differential drive. The 2 wheels by themselves, not like connected, and it's pretty much we're doing a quasi front wheel drive setup for the robot.
The components of the robot were printed over a series of days on an Ender 3 printer in PLA plus filament. This material was selected due to its durability and availability. The robot was then sanded and painted with a mixture of spray and acrylic paint. The design was inspired by a turtle from the popular game Minecraft due to the simplistic but fun look that the Minecraft turtle offered.
Moving on to the electronics portion of our tortoise-themed robot, here's the updated system diagram. We are still using an Arduino Nano as the microcontroller for our project, which controls our 3 outputs: the servo motor directly and the 2 DC motors through the L298N motor driver for speed and direction control. These outputs are controlled by the input of a camera board. We updated our power supplies to use 6-volt rechargeable batteries. As you can see, we have one nickel metal hydride battery, which provides the largest amount of power at 2400 milliamp hours because each motor draws much current. We also plan to use 2 nickel cadmium batteries, providing 700 milliamp hours to the MCU and camera board as well as to the servo motor. However, this was not enough voltage for the camera board, and we ended up using a 9-volt battery for the camera and MCU during the demo.
For the electronic adjustments of our project, our main issues lied in the camera and power sources. The first camera we used was the ESP32 cam, which our programmer was able to run with live feed viewing. The issue was that the frame rate for image processing was entirely too slow, about 12.5 FPS, and even slower depending on what SD card we used. There is also a huge learning curve regarding image processing using Arduino, which would require our software developer to fully learn the Raspberry Pi environment, which would also push our budget and time constraint. From this, we decided to shift over to the Pixie 2 Cam, which is a smart vision camera that has built-in functions and capabilities to do computer vision, excelling in color recognition, which is exactly what we needed. As for the power, our main struggle was the strength of connections, which was hindered by having 3 different batteries. In order to turn on the system, it required us to replug the wires every time we reset it, and it was very easy to short or miss wires during the whole testing phase. This led to us burning our system due to too much current flowing back and forth. In future attempts, with a greater budget, we would invest in a larger battery with 7 volts that would increase the consistency of voltage going through our microcontroller. A switch would also be more reliable in terms of turning the system on and off without having to replug the whole system.
The robot's software relies on an internal state machine with 3 separate states: Q0, the head retracted, where it waits for an object of the target color; Q1, the head extended, but it does not see an object of the correct color; and Q2, the head is extended and an object is detected. It may only move in Q2. The vision processing causes the transition to each of these states by using a color-based filtering algorithm to detect objects called the Color Connected Components, or CCC, algorithm. To navigate, our robot calculates the distance of the largest detected object of the target color from the center X coordinate of the camera's view. Once the object is on screen but past a certain threshold of distance from the center, the motor of the opposite side activates to aim the robot closer to the center of the target object. When the target object is detected within the threshold of the center, both motors are activated to drive the tortoise closer to the object. While our end result was not perfect, our concept was strong, and the time we spent working on the building process taught us valuable lessons about electronics, coding, and manufacturing. Demos for our robot are available in the description. Thank you for your time.